I started. Is it okay?
Yes.
Okay. Good afternoon, everybody. Let's continue with this course. I want only to remind you that tomorrow we have 1 hour our lesson, and the second hour will be devoted to the test. So in the first hour I will present you artificial intelligence applied to software testing, and during the second hour I believe that they have 1 hour mission or 15 minutes 15 minutes for completing the test. That will be done by Google Form. It will be a Google Form where you can complete your test. Okay. Today I will show you in the first hour of the lesson, I will present you introduction to random testing. And after, I will show you in the second part of the lesson, or the talk, I will present you how random testing can be applied to the exploratory testing. Okay, yesterday we saw or we analyzed the random testing, the online testing technique, and we observed that when we are in a given state, we can follow or we can trigger a specific event, okay, in order to reach another state. Like the famous example of the ecological park, when I am in a place where I can choose between 2 or more paths to follow, I can, by random, I can choose one of these paths, okay? So, according to the standard, I don't know if you know the standard. If you don't know the standard, I suggest you to study and to analyze it. The standard ISO 29119, that is the standard of software testing. According to the standard, the random testing is defined as a testing technique where the input values are randomly selected from a set of possible values. As an example, let's consider a function whose argument, imagine a function that has just one argument that is an integer value. By random testing, we choose integer values by random. Okay? So, when we use random testing, we should start from a probabilistic distribution of the input for generating the input value. So, in general, when I have to collect or select input values by random, the way in which the random values are selected follow a given input distribution. So, why random testing is very important? Because random testing is very easy to use, it's fully automated, and it can be quickly deployed. So if you go on the web, if you search on Google, there are many random testing tools that you can use both in research and in industry too. So this is why random testing is very popular among the practitioners in industry. So usually in industry use a lot random testing for different goals, as an example for vulnerability testing, for prediction testing, or in some cases for functional testing. Okay, What do you know the pseudorandom? What pseudorandom means? As an example, if we consider the pure nature of a random process, a random process that is pure random process is the if when you launch a coin, okay? If you launch a coin, it's a pure random. If we try to generate random values with our PC, we have an algorithm that seems to us that it generates random values. And in this case, we can talk about pseudo random, okay? So this is why we talk about random testing, because the algorithm that run on our PC that seems to generate random values actually use deterministic methods. Okay, so when we run an algorithm, is actually a deterministic method instead of a non-deterministic method or a non-deterministic process like the launch of a coin. Okay. So this is why I wrote in the second point of the slide that pseudo-random sequences are by definition not truly random. Okay. When you find in a paper that the approach that is followed or that is present in that paper is random, actually the approach is pseudo-random because the values are generated by an algorithm that actually is non-deterministic. Okay. So, but how we can change the way the random values are generated? We can choose a sampling distribution. So if we change the sampling distribution, we can define how the random values are generated from the scratch. Okay. So as an example, if we define if we want to define a random values or we want to select random values, we can define a profile. Okay. Imagine that we want to test a GUI of an application. Okay, by random. We may collect or we may design or we may we may define or collect a priori we can define a profile that reflects the expected usage of the GUI. Okay, imagine that we want to analyze or we want to produce random values for a GUI. We can choose or we can define a profile of usage of that GUI. Okay, as an example, if I want to define a profile usage for Word, usually the user goes on the menu, click on File, and then click on Open, then write something, then select a text and change the attribute of the text, like the size of the characters, the type of the characters, the color of the characters. We have a profile, okay? And according to this profile, we can decide to generate random values from this profile. Or, on the contrary, we can decide to define random values that do not adhere to that profile in order to generate values that are unexpected by the programmer, by the programmer, by the developer. Because in this way we can try to trigger the application with events or with inputs that are not expected by the developer. Okay? But usually in the many papers, if the profile in the paper or in the approach is not defined, the testing strategy or the strategy for selecting values from for a distribution actually is used a uniform sampling for profile, okay, where all the values has the same probability to be selected from the initial set. Okay, so if I have a set, the uniform sampling profile means that all the values of the starting set has the same probability to be selected. Okay. Now, in literature, there are different have been proposed different random testing techniques, and as I did in this course, I try to provide you pointers to good papers that you can use as starting point. I want to suggest you this paper that is published by Mariani, Pizzi, and others, where the authors tried to provide the classification of the proposed random testing techniques. Okay. So, in this, according to this classification, we can consider pure random testing, where the test inputs are generated randomly with a uniform probability. Okay. Then we have an extension, or we have an improvement of the pure random testing that is defined adaptive random testing, or ART. So the ART is a random testing technique that has been proposed to improve the failure detection effectiveness of random testing. So the adaptive random testing, so if we see at the definition, adaptive, it means that we have a random testing approach that adapts the selection of random values. Okay, so the adaptive random testing approach is a way for improving the capability of pure random testing techniques to detect the faults. Okay, and the main idea that is at the basis of adaptive random testing is based by considering the diversity of test cases. So the adaptive random testing is based started from an analysis of different or various empirical observation. Okay, so if you consider a program, you can see that a program there are different regions where you have faults and regions where you have not faults. regions of inputs that may generate false, a region of inputs where you cannot generate false. Imagine that you have a function f with two inputs, 1 and 2. Okay, these are the we can represent on the graph the values assumed by 1 and 2, and there could be regions where I have faults, or regions where we have no faults. So, by empirical evidence, by empirical analysis, the authors observed that there are regions where near input values can generate faults. So, in the sense, it means is based on the observation if I have an input here, with an high probability, another input that is here can generate a fault, right? Now, the adaptive random testing starts from this intuition. And imagine that we have a input here that is chosen by random, okay? And this input does not provide a fault. The next input. As for the next input, you expect that the next input will be here, or you expect that the next input is closer, or it is far away from the current input. Okay, I repeat. This input is generated by random, okay? 3 and 5. And I have this input here. It does not generate a fault. I want to adapt my random testing technique, okay? You expect that the next input will be here, that is very closer, or far away, according to the intuition.
I guess that it should be far away.
Yeah, it should be far away because since here I did not have a fault, probably according to this intuition, other inputs that are near will not provide a fault. So I try to go more distant. I try to go far away. Okay? So if I have here and I found the false, okay, if I find the fault here, I can decide to stay here, but I can try to go far away because probably I already explored this state. Right? You understand? Okay. If there are questions?
No questions yet.
Okay. And this is the intuition that is at the basis of the adaptive random testing. So the goal is to adapt the random choice by selecting input that are distant each other. Okay? Then we have another approach that is called guided random testing, also known as GRT. Okay, GRT is a very interesting approach where the random testing is supported by static analysis, in the sense that before executing the random testing, the random testing approaches or tools reverse engineering the source code for understanding the space of the possible inputs. To understand which kind of inputs we want if I don't know anything about the application under test, and I can analyze the source code for defining the space of the inputs from which I will select by random the possible values. Okay. Now we have in this approach another definition that is called fuzz testing techniques that are based on approaches where the valid inputs are mutated. So I know which are the valid inputs, and I can apply random mutation to the valid inputs. This is an approach, this is only a graphical representation on how adaptive random testing works, and you have here the paper that introduced for the first time, or the main, or the most important, from my point of view, paper where adaptive random testing is introduced. And this is the approach of guided random testing that has been provided in this paper. If you see, I don't want to be much more in details. We have two phases. The first phase is called the static, where we statically analyze the system under test. Okay, and we, from the static phase, we collect information that can be used at runtime where a random testing approach can be executed. Okay. If you want to go more in details on this approach, you can see, or you can study the paper that I reported on the slide. Okay. So as an example, in the constant mining that is static, the constants are extracted from the suit for global usage, such as or for each usage as input. Okay, so you can analyze the code statically for understanding, as an example, the type of the global variable or the type of inputs and so on. Question? It's clear? Okay. Usually, random testing is also known as monkey testing. Okay, so we have 3 monkeys, and there is a classification on the basis of the knowledge that the monkey has of the application under test. Okay, so we have dumb monkey, smart monkey, a brilliant monkey test. In dumb monkey, so usually I want to point out one thing, that the difference between dumb, smart, and brilliant is with respect to the point of view of the tester. Okay, so in dumb testing, the testers or the single tester does not have any knowledge of the product or of the software that the tester that he has to test. Okay, or the tester does not have any idea of the application. Okay, no idea of the user interface features, or the tester does not know what is a valid input or a not valid input. Okay, let's do an example. Let's consider okay, I have this user interface. Okay, Junior, for your point of view, what is this user interface?
It's a calculator.
It's a calculator. For you, yeah, for you, it's a calculator. And how do you test this calculator?
I insert the number.
Okay, you insert a number, right?
Yeah.
Okay, you insert, as an example, 1, you insert 1, and then you click one of them, right? Okay. In this case, you are not a dumb monkey, right? You are not a dumb monkey. Why you are not a dumb monkey? Because you are in a level of abstraction where you expect what the user interface is. You are using the user interface starting from the hypothesis that this is a calculator. A dumb monkey does not know that this is a calculator. And dumb monkey works in this way. It clicks on plus. It clicks in division. Then he puts here A, F, G. Then click minus. Then he can set here, put 0 here, and click on divide. And you have null. You have a division between null and 0. Probably we, as a developer, never tried this combination of events, right? So, a dumb monkey does not know anything of the application, or even if the monkey knows, or the tester knows, or have some idea of the application, the tester does not consider the type of application. It's clear, Junior?
Yeah.
So this is why I asked you what you inserted. You insert 2 numbers, and now I want to ask you why you don't try. We do not try string. Why we do not try characters? Why we do not try special characters? Why we do not try null? Why we do not try to click multiple times the plus? So, like a monkey, we can try the application without having no idea of the application under test. And believe me, you can find many failures of the application by using this approach. Question?
I was thinking on, because for the point of view of a human, it's more easy to think on the head path than in the wrong way. And so if we assume that the tester has no knowledge about software testing, probably he will follow the intuition of junior. But
probably if you consider if you consider the type of application, probably you are moving from dumb monkey to smart monkey. So in dumb monkey, you do not have any information of the application under test, or from another point of view, in dumb monkey, you do not want to have an idea of the application. Even if you have an idea of the application, you do not use this knowledge for generating random values. Okay? And if you do not have an idea of what the application is, you may generate invalid inputs or inputs that may present or may trigger a fault or a failure with respect to the other type of monkeys where you know the type of the application under test. Okay?
my point is sometimes we are brilliant monkeys, but we act like dumb monkeys.
Yes. We go on with the definition. Okay. So in smart testing, the tester have a good knowledge of the application. Okay, imagine that this is the application, and we have a good knowledge of the application. Okay, we know. The tester know exactly the functionality of the product. So, and the tester should have knowledge of valid and invalid inputs. As an example here, probably an invalid input is A, B, C. Since I expect here a number that could be an integer or a real, but for sure an invalid input is a string, right? Okay. But if we know a valid input, we can use the invalid input as an example in penetration testing for trying to break the system. Okay? If I know the valid input or the invalid input, I can exploit the invalid input, or I can exploit the random generation of invalid input for trying to break the system. As an example, if I know that strings are invalid inputs, I can try to generate by random strings. It's not clear?
Yes.
If you know that here strings are, in this context, strings are invalid inputs, okay? Because in the calculator, you do not expect to write a string, okay? I can use this knowledge for generating random values of invalid inputs. And I try to stress the application in this way. So, the problem is that the tester should, in this case, should be able to build an infrastructure that is able to trace the bugs. Because if the application crashes or the application breaks, we need to know what is the sequence of inputs that generated the crash. Because, okay, I found the crash, But when I find the crash, my problem is to debug the application in order to resolve the crash, or in order to resolve the failure. I found the crash. Probably, if the application here accepts a string, I have to understand why the application accepted the string. I have to fix this bug. Okay. Brilliant is one level up of Smart Monkey. I believe that the difference is very slight. In this case, in Brilliant Monkey, in this case, the tester not only checks that the feature or the functionality of the application is validated by providing valid input, but it has a special focus on finding bugs, and the testers are sharp enough for reporting the bug if it is found during brilliant testing. So the brilliant testing is a Smart Monkey with the capability of reporting the bug and to fix the bugs, okay? To report the failures, the bug, and to fix the bug. And usually it is done as the perfect perspective of the end user. Tell me, Junior.
No, okay. The dumb monkey is just for formatting the valid and invalid inputs from
Smart Monkey?
Oh, the dumb monkey. The brilliant.
No, the dumb monkey, you generate values without having any information of the application under test. In Smart Monkey and Brilliant Monkey, you have this information, and you can exploit this information for generating random values. Okay? An example is that you can partition the input in valid and invalid, and after the partitioning, you can choose to select the random values from valid inputs or random values from invalid inputs. It's a choice. The main idea is that you have the knowledge of the application under test. You know how the application under test works, and you know what you expect from the application under test. And you can use this information for generating random values. Okay? It depends on the knowledge that you have of the application.
Domenico. Alex Federico sends a question. The monkey test else could he assist test them also would the system buttons.
Yes. Yes. Who is the name?
Alex Federico.
Oh, okay. Alex. Okay, Alex. Yeah. As we will see in the next hour, random values or random testing in GUI-based testing is a sequence of random events that you trigger on the graphical user interface. As an example, by Express or by other GUI interaction or GUI-based tools, GUI-based testing tools. Sorry, I don't know if answered to your question, Alex.
Okay, more one question.
So next week. Okay, and I don't know I don't understand what is the question here.
Me too.
Marcelo, I see that your Sentence is an affirmation. I do not understand what is the question because I don't see the quote mark. It's only if it's only an observation. Okay, maybe I agree with you. Okay.
Which tool is better in this case? To perform this.
Okay, it depends. It depends if you are testing the single function or if you are testing the GUI. Okay, for the single function, there are different tools like Rundup or EvoSuites that generates the random values. And as an example, you can define how to select by random the three points of the isosceles or equilateral triangle. I don't know if you have the GUI for this kind of problem, you have to move to another tool that interacts with the GUI of the application. As an example, my Android Reaper or Dynodroid, or you can write the testing with the Puma. There are other tools or that can help you in this in the resolution of this problem. And I don't know if my answer is sufficient for you. Please tell me in the chat.
Keep going.
Okay. Okay. Now, what? It's okay for Marcelo?
Not yet.
Okay. Okay. We wait for Marcelo. Okay. As I'm trying to telling you from the beginning, there is no a silver bullet. Okay. So random testing is not a silver bullet. My tool is not a silver bullet. Model-based testing is not a silver bullet. As a tester, we have to know the techniques, the methodologies, and the tools, and we have to use the most suitable in that case. And in some cases, the best solution is a combination of solutions. Okay, so it's okay, Marcelo. That is not okay. Okay, which are the pros and the cons and the weaknesses of random testing? As an example, random testing is cheap. You can, as I said in Marcelo, there are many open source tools like Rundup and EvoSuite that you can use for random testing of applications written in Java or in C. There are Monkey, that is the tools that Android distribute with the Android SDK. So you can use a Monkey, and you have a Monkey that interact with the application under test. So there are many tools. So the problem is, if you don't find a tool for your purposes, it's very easy to implement a new one. Okay. So also, if as an example in your case, Stefano, if you want to test a virtual reality software system by sending random events, it's very easy because you have only to by random send pitch, probably is the basic event on virtual realities of the system, and you can send them by random. Okay, and it is easy to find random testing tools. Okay, so it does not need much skill in software testing, so you have only to generate random and find bugs and find crashes and failures in the application. It does not need knowledge of the application under test, so it's clear. Tools do not need too much configuration effort. You can launch the tool, and the tool works for you. And it's very important. It may generate unexpected inputs or sequences of inputs that may cause the system crash. So, as I showed in this example, a random tool or a random testing technique may generate a sequence of events that us as human probably will not define a tool. Which are the consequences? Which are the weaknesses point of random testing? When I found an error, it's very difficult to debug the system under test because you have sequences of events. Imagine that you have a sequence of 100 of events, and probably the sequence of events that generated the fault is limited to 3 events. So it's very difficult to understand what is the cause, what is the sequence of events or the sequence of inputs that generated the crash. So imagine that you have a log of all of the sequences that have been submitted to the application under test, and then you have a crash. The problem is, I see the log, and it's very difficult to understand what is the sequence of events that you have to replicate to understand something about the system under test. Okay, imagine that if I have plus, minus, then I have 7, 8, 7, 8, 7, 8, then I have a 0, division, no pointer exception, arithmetic exception, division by 0. I have the sequence of events, and only the last 3 events generated the crash. I have a very long log trace that I have to analyze. Okay? Okay, as I said before, it's not easy to replicate in regression testing and compatibility testing the sequence of events. And the problem is that the random testing is mainly used for crash testing or in some cases for penetration testing. So it's very difficult to use this approach for testing other quality attributes of the software under test. Okay, so after only 10 minutes, and because I need some space for explaining other slides. Okay.
Marcelo, it was clear.
Okay. Thank you, Marcelo. Thank you so much.
Okay.
Okay, guys. Now that we knows more or less what random testing does, so in random testing we generate random values, random input values. We move to random GUI testing. Okay, as we discussed in these days, a test case, a GUI-based test case, is made by sequence of events. Now, if we consider a graphical user interface, the random GUI testing, in random GUI testing, a test case is given by sequences of random events on the GUI. So, in random GUI testing or in random GUI-based testing, we have a monkey, so a robot that send events on the GUI, and basically we in IntelliJ monkey is used for two purposes. One, for finding crashes on the application, or for performance testing. As an example, from a point of view, from a site, one site, you have a monkey that interacts with the GUI. On the other side, you have a tracer. And with the tracer, you can collect information about the drift of the battery, the CPU usage, the memory usage, the network traffic, and as we said at the first lesson, we are in the context of GUI-based testing. We are stressing the application to the GUI, and we are monitoring the resources of the application. And after that, we traced all the behavior. As an example, we can understand if the application drifts the battery, if the application needs a lot of CPU usage or memory usage, or we can analyze the network traffic that the application needs with the server. Okay? Now, there are many tools implemented monkey fast testing techniques. One of these tools is Android Reaper. It's free downloadable from my website, but it's now I'm going to release a new version of Android Reaper that is a Jugular that we will discuss tomorrow that apply AI to artificial intelligence to GUI exploration. And but there are many tools in IntelliJ. One of these is Sapiens, another one is Dynoroid. Okay, so we develop many of these tools and we compare each other these tools. Okay, but one of these is Android. Android Reaper. Okay, I want to talk to you about one problem. When stop the monkey? Okay, so okay, usually this is the algorithm that is used by a random GUI random testing. Usually you configure the parameters. As an example, you put the application in a given precondition. You define which are the events that you want to fire. You define the delay between two consecutive events. And these are the main parameters that the tester configure before launching, before opening the monkey on the application under test. Okay. Once the tester configures the tool, as an example, the tester said, okay, I want a random event after each 100 milliseconds or 200 milliseconds, so I want to wait 1 second between consecutive events. I want to put the application in a given state before starting the exploration, and so on. Now, the process continues until you reach a termination criteria, a termination point. Now, I want to, before going with the on with the slides, I want to discuss with you about some intuition. Okay. Now, okay, we call Uber and go again in the ecological park. Okay. I arrive in the ecological park and I have 3 ways. Now, I'm not building the model. I go random. So I don't know if the event has been triggered before or not. I don't know if I visited or not that state. So imagine that I go by random. I select this event. So I select this street. That is the same of triggering an event on the user interface. Okay? So we have the parallel, the state, that is the place of the ecological park, and the GUI of the application. We have this mapping. The state that I choose to work is the event that I fire on the application. Okay? Then I reach here another state where I have 2 ways. I choose this one. This is event 1 and this is event 2. And I reach this state. Okay? Now I have 2 ways. And I choose this one. When I perform this plot, I return here. Okay? Since I am by random, and the choose of the event, each event has the same probability to be selected, right? Because it's pseudo-random, or in base random, the distribution of probability is uniform. It may happen that I follow again spot, or I follow again spot. And if I define a termination criteria based on the time, what may happen? May happen that in a predefined time or slot of time, I execute or I navigate always the same path. Okay, this is a problem. So let's try to move from the GUI state, so from the exploration of the ecological park through the GUI-based testing. Okay, from one side, we have the GUI. On the other side, we have the code of the application. So, if I fire events on the GUI, I cover, that is, I execute code of the application under test, right? If I trigger events, I'm calling event address. Event address is code. Probably the event address calls other functions, and on the basis of the input that I put on the GUI, I cover code. And usually the metric that is used is the covered statement percentage. That is the number of statements that are executed over the number of statements of the output. Okay? As an example, if our code is made by 200 blocks and I cover 100 blocks, the covered statement percentage is the 50%. Right? I covered the 50% of the code. Okay? Okay. So this is the situation. I click by random and I measure the code coverage. Okay? Now, why this? Because as we see in the first lesson, one of the metrics for evaluating the effectiveness of a testing technique is the number of faults, or if I do not know this metric, another metric is the number of covered state. Because there are papers where it's demonstrated that there is a correlation between the number of covered states and the fault detection capability. In other sense, if I cover more code, probably I will discover more faults. Okay? It's clear? If I cover one line of code over 1,000 lines of code, I have less probability to discover faults if I execute 900 lines of code, right? Okay. So let's consider this graph. Okay. We have the number of file events. As an example, one of the termination criteria is related to define at the beginning the maximum number of events. Okay, imagine that I want to fire 2,000 of events. I run the first execution, then I run the second execution. It's by random, okay? So then I run the third execution. What you see here? What, as a researcher, as a tester, what do you see? What is the observation?
They look pretty similar.
What I expect from a testing process? I expect that the testing process has always the same behavior. What I have here that the coverage is defined by the chance. In some cases, I reach the 79. In some cases, I reach the 80%. In some cases, I reach the 82%. Probably, if I launch another execution, I reach another coverage percentage, right? So it seems that the effectiveness of the random testing depends by the choice of the tester. Because if the tester here chooses 700, I stay here. So, or if I choose 300, the coverage is here. It depends on the choice of the tester, right? Now, imagine that I choose to perform a lot of events. What do you observe? That I reach, okay, what do you observe? 1 minute.
After a number of execution, they converge.
Yeah.
Probably because they
Probably.
explored all this space
Yeah.
of
Yeah.
state of.
So you see that if I fix a testing time or I fix too much events, I have low efficiency because I waste my time in testing the application, and this time here is not necessary because I reached this point. Okay, on the basis of this observation, we proposed a testing approach. Huh? We propose a testing approach because from this slide, we may observe that if I run in parallel different random testing processes, probably together they will reach a termination point. It's if I write here, it's visible.
Yes.
Okay. Let's consider the ecological park. Okay, I have here, and imagine that we start. There is Domenico, Junior, Lisa, and Stefano, and we start by run. If a professor that is there with a walkie-talkie ask us, did you visit this point? Did you visit this point? Probably by the combination of 4 random exploration, we converge and we explore all the ecological park. So we used this solution, and we provided a testing process that automatically stops its execution at a point that represents an optimal trade-off between the effectiveness and the cost of the testing process. Okay? A point where the test adequacy is maximized in the sense that we covered as much as possible, and no testing effort is wasted. So we want to stop here. So the basic idea is that we run in parallel different random testing, and we stop when all the random testing processes cover the same code. So it is based on 2 theoretical phenomena. The first one is the saturation point. So if you have a random process, if you run a random process for a long time, the random process reaches a saturation. This is called as saturation point. And we want to use the saturation point as the termination point. It's correct? So when I reach the saturation, I want to stop. Because if I continue to do the exploration, I will not discover other code. I will not cover other code. And probably at this point, I can change the configuration and start another process for discovering other code. It's clear, guys?
Yeah.
This is the intuition. I want to explore a space by random, but we collaborate in the exploration of the space. This is the idea. The second phenomenon is the predictability property of a model of a monkey fuzzy testing. So this is this second phenomenon is described in this other paper, that is a great paper reporting the theoretical aspect of random testing, and I suggest you to read this paper if you are interested in this kind of in this kind of testing. At the basic of this idea of this phenomenon, I don't report here the mathematical aspect and so on. I want to report the intuition. If we have two test cases that are random, at the limit, they tend to reach the same test adequacy. Here, so in other words, the difference in coverage or the difference in adequacy of two random testing techniques or two random testing processes tends to 0, right? If I consider difference here at the saturation point, the difference is 0. Junior, it's clear? This is the difference between this. Okay, this is the difference between red and green. If you see, the difference tends to 0. Here, the difference is 0.
Yeah.
It's correct? So, we exploited this two theoretical phenomenon to propose a solution. Our process exploited the definition of predictability. This is the phenomenon. The predictability seems that for a long time, at the limit for t that tends to infinite, the difference tends to 0. This is the predictability. I can predict that at a long time, the difference is 0. It means that the two processes reach the same adequacy. Right? Okay, and we used this potential saturation point. Why potential? Because it depends on how I reach the random. It means that in the ecological part, if me, you, Stefano, and Michel discover these places, since we are going by random, it may happen that some places are not covered. It's random. But I have the probability that we agree on the same exploration. And probably we leave outside only a little percentage. Right? Okay, so the determination of the potential saturation point is based on the simultaneous execution of several random testing sessions. So I run in parallel different random testing sessions that are controlled, that are supervised, and the overall process is stopped when all or the union, now we understand another point, when all of us or all the random processes reach the same saturation. It's like here, we go to the park and we explore by random. And we talk each other by walkie-talkies. You know what is walkie-talkie? Okay. And we say, okay, I covered these places. Okay, I covered these places. Do we cover all the places? Yes, okay. There are no more to discover. If Stefano say, no, I covered another space. Okay, let's continue to explore. If you discover the place that we three did not encounter, we have to continue the exploration. Okay? This is the process. So if you see here, this is our process. We run 3 sequences. In this case, we call this a reliability zone, because as a tester, this zone is not reliable, because it depends on the choice of the tester. You see here, if I launch or if I execute more execution, I have different results. As a tester, I want that when I execute a testing process, I expect to have always the same result. I have to trust in my testing process, right? If I continue here, I have a not efficient zone, because here I waste time, I waste resources, I waste energy, okay? Because my PC are running, so I have a cost. I want to stop here, where there is a saturation effect. We call this as saturation point, where I use the predictability, because I know from the theory that if I launch 2 or more testing processes at the end, when t tends to infinite, at least the difference between the adequacies tends to 0. Okay, so we use this kind of metric. Now I try to explain you. At the numerator, I have the union of the covered statements. It means that if junior covers this and this, Stevao covers this, me and Miser cover this, the union is all this. So we can consider the union. So at the end, to have the final metrics, we have to consider the union of the states or of the statements of the code that together cover it. Okay? So this is the metric. The union of all the set of covered statements over the number of the statements of the IoT. Let's consider. I have this testing process that covers the 40%, okay? And another one that covers the 40%, right? The union is not 80%, but can be 70% or 40%. Why? Because it could be that we have some code that is covered by both the testing processes. You understand this?
Yeah.
Okay? Imagine that I have an if here that is covered by both. The union is not the sum. We have to consider the union of the statements. Right, guys? As an example, I can have the worst case where the 2 testing session covers the same code. Yeah. I'm not like in this case, because as an example, you and Stevao, it means this is exactly if we consider the parallel with the ecological park, it means that you and Stevao at the end covered or visited the same part of the ecological park, right? So this is the metric that we have to consider. Now, this is the algorithm, but the algorithm is provided in a paper that okay, oh, sorry. No, this is not here. Okay, but I think you find the paper, probably I do. So, don't consider the algorithm now because we are all tired, but let's see the main point of the algorithm. I launch R cap K, sorry, cap in Italian, K testing sessions, okay? 1, 2, 3, 4, N. Then while the K sessions do not reach the same coverage, okay? Each session fires a new event. It means that in parallel, I have different random testing sessions that continue until all the testing sessions do not reach the same coverage. And at each iteration, I evaluate the termination condition. Okay? Okay. We have two definitions here. The algorithm produces two outputs. One is the termination point. That is the minimum number of events at which the termination condition is verified. Okay? Termination point. Termination point is, here is how much? Is 3,700, right? Okay, sorry, I don't see that from here. And the termination level is the level of percentage that is the coverage statement percentage reached by all the K testing sessions. Okay. In red, we have the union. Okay. The union. It means that the union of this is here. When I stop, when all the testing session explored the same code, right? Because they all reach the union of the coverage. This is my termination point. I implemented this in this infrastructure. As an example, I have this component. So we are software engineers, so we have to deploy and to we have to design this algorithm, this process. Sorry, we have to design the tool supporting this process. This is my this is what I performed. I have a supervisor that controls the execution of 2 or more testing devices. Okay, so it was made for Android, but in another paper that was published on transaction, we implemented the same approach also for unit-based testing. Okay, so we demonstrated that this approach works on GUI and works also on testing of single functions. Okay, but why I don't report it? Okay, Michel, you have to distribute the slides?
Not yet.
Not okay, because after I sent you the new version with the link to my paper. Okay.
Okay.
Now, we in the paper that I will, but we can find my paper in my curriculum. So it was this paper was these results were published in Mobile Soft, that is a conference on mobile testing. I tried to understand, we tried to understand if the testing process is able to reach the saturation at the termination point. It means that there is a why the termination level is not 100%. As an example, in this example, I do not reach the 100%. Why? Okay, we did it on 18 open source Android application, and we analyzed the residual percentage. As an example, if this is the executed code, that is this one, okay, that is a residual percentage, right? If the executed code is 80%, the residual percentage is 20%, right, guys? Okay, so if we don't reach the 100%, we try to understand why we do not reach the 100%. Do you have some intuition of why we do not reach the 100%?
Maybe you have some unreachable.
Grades. Just great. It is the not executed code because, as an example, is not unreachable. It's that good. But there is a problem here throughout. The sum between executed code and unreachable code, I have a little percentage that could be reached, but I did not reach. Why? And I spent a lot of time to analyze the code, to analyze the results, and understand that what I see now, it is reported next slide. So then we jump the slide. So I tell you a story because at this time we are tired. The reachable code is mainly due to two main reasons. The first reason is that, okay, it's random. And I have a very few parts of the code that in this process, all the parallel execution did not reach because they were random. But I have another observation. The unreachable code, so this reachable code that were not executed, depends on the configuration of the testing tool. As an example, if I configure the tool to perform only clicks, probably I reach all the code that is covered by click. The other code is not covered because I did not consider that event. Because remember that I have a gap here because I'm triggering the GUI and I'm measuring the code. So the code that is covered depends on how I interact with the GUI. It's clear? So how? The way you configure. As an example, if I change the initial precondition, I can reach some part of the code. If I have an application that interacts with the database server and the database server is empty, probably I can interact only with the part of the application. If I have data in the database, probably I can execute other part of the code. So we understand that if these are the experimental procedure, and we observe that in all the cases the proposed testing process was able to reach the saturation at the termination point. In most of the cases, it depends that we reached all the code that can be reached. Okay, and we observed that the main factors affecting the effectiveness of the proposed testing process were the precondition of the LT, the configuration of the testing platform, so the configuration of the tool, the limitation and the configuration of the tool. So we have some limitations. As an example, my Android Reaper was not able to perform some events, like the arrive of a telephone call. Imagine that I am working or I'm interacting with the GUI, and during the usage a call arrives, the application is stopped, so other code is executed. And since my tool is not able to find this event, I have a limitation, and that code can never be covered because I have a limitation in the tool. And it can use this approach for understanding or for discovering the unreachable statement. So the code that is not covered could be unreachable, could be that code. Okay? So then I have another intuition. Okay. Here we stop the execution, right? When all the testing processes reach the coverage, the union, right, guys? You remember when me, Stevao, Misen, and Junior cover the same coverage, right? When all of us visited all the ecological park, right? But why we cannot stop when the first one of us will covers the same the union. Sorry, when the first one covers all the possible code of the application, it means that here I stop when the first one of us has discovered the union of the places of the ecological park. So I don't wait when all of us cover all the places, but I stop when the first one covers all the states. In other sense, I stop when the more smart of us or the more lucky of us covers the same, all the reachable code or all the reachable states of the ecological park. Do you understand this intuition?
Yeah.
Here, I have to wait that all the sessions cover the union. It means that covers the reachable statement. Here, I stop when the first random session covers the union.
By doing that, you are not
Sure that maybe if I go on, there could be another.
I mean, since I'm performing some events different than you in orders different than you, maybe the fact that I'm performing the events in a different order maybe trigger
New events.
Yeah.
New events? Yeah, sure, it may, but it's a choice.
Okay,
It's a choice.
It's a choice.
And but I do not want to waste this time.
Okay.
But as an example, your case could happen.
Yeah.
But since your case have a very few probability, I don't want to wait a lot of time to trigger only that type of event.
Okay.
But I have the same intuition or the same issue indeed, I performed an experimentation. I performed an experimentation, and to validate this intuition, we compared the two approaches. And we observed that in most of the cases, the two approaches reached the same saturation level with a great reduction of the fired events. There are cases where this therapy star reached a less covered less code with respect to therapy, but it was only I observed only few cases for this situation. Okay, now, this is the transaction. We compared these two approaches that are called AEQ and AEO. It means that AEQ is one, and AEO is this one. Okay, so this is when all the processes reach the same coverage. Here, I stop only when the first one reaches the same coverage. Okay, and we compared, guys, with all the termination points that have been proposed in literature. As an example, T1, you stop after testing time in minutes for testing session that is equal to the number of classes of the application under test. This is a termination point. As an example, if my testing process if my software under test has 5 classes, I have to wait 5 minutes. Okay. In this case, 2 times the number of classes. So if you have 5 classes, you have to wait 10 minutes. Okay. 7, it's the same. You have to wait 7 times. T50 is you stop when you have at least 50% of iteration that have been executed without an increase of the coverage. Okay, so if you don't see a increase of the coverage after the 50% of time, you have to stop the execution. Okay, we compared all these execution, all these termination criteria, and what we see, this is the union. We see that if you stop before, as I have T50, you are here in the unpredictable or in this unpredictable zone. If you see, the most lucky approach reach the saturation. If you consider T1 and T2, you have you lost a lot of time. So you are here in the zone where the process is ineffective. Okay? Oh, inefficient, sorry. So both the criteria could be considered alternative to time-based criteria. So from one side, we have a criteria that are based on the choice of the time, and they depends on the choice of the tester. This approach is objective in the sense that it does not suppose or it does not rely on the choice of the tester. Okay?
Domenico.
Yeah.
Sorry. Must have sent a question.
Yeah.
About this topic.
Yeah, it could be used. If you use a random approach, yeah, you can use this approach also for measuring this kind of quality attributes. Okay, yeah, it could be used. I did not do, but yeah, if you exploit random testing, it could be considered as a termination point. Yeah. Okay. Some observation. I am very critical with myself. So this process, it's not a silver bullet. So for me, it's another possibility to stop random testing. But I propose this approach, and I know that this approach has some issues. Okay? As an example, one, the implementation, you have to implement this infrastructure. Okay? So you have to run multiple random sessions, and you have to combine their execution in order to evaluate the mesh criteria. So you have to develop a testing infrastructure. Okay? It's not easy. So yeah, it's not so difficult, but you do not find tools that perform this for you. You need you need more than one robots. Okay, I did this experimentation with the robot provided by Android, and I implemented the infrastructure in 2 days. Okay, so I did not waste so much time. I used the cobertura for measuring the code coverage. So I used these tools, and I implemented the infrastructure. So it's not so difficult. So you have to choose an upper bounded metric, guys, because if the metric is not upper bounded, you have not a termination point. You understand? Mm-hmm. So if the metric evolves and the metric tends to infinite, you cannot use that metric for stopping the process, because the termination point could be at infinite. You can have a function that diverges. You need an upper bounded metric. This is why in this process I used the code coverage, because the code coverage is upper bounded. Okay? Okay, you need to implement more question. From your point of view, does the number of parallel execution influence the results? As an example, if only me and Stevao explore the ecological park. If we as Stevao explore the ecological park by using this approach, and we have some result, okay, we cover some part of the ecological park. If I add other people, so I add Junior, I add Mise, I add Delamaro, I add your student, the number of people exploring can influence the results?
My intuition is that it can influence, but just at some point after that, adding a number more.
There is a class here, no?
No, I don't know.
Okay.
Add more machines to the process would not influence. But
Okay.
I guess in the beginning, more.
Okay. We asked this, and we observed that yes, the number of parallel execution influences the results. If we consider few, as an example, only 2 people, the termination level or at the code coverage is not maximized because we cover the same part of the application and we reach in a very few time the same coverage. So I stop the execution, but I do not reach the maximum. Can I continue, Mixel, or the?
No. 10 minutes, okay. 10 minutes.
Okay. If we use too much session, so imagine that we try to explore the ecological park by calling all the students of the University of Sao Paulo, maybe I am using unnecessary resources, okay? So we observed that, yeah, the number of processes in parallel can depend on the complexity of the application. This is an open point now. I'm trying to understand what is the best number of parallel execution, but we observed that 8 parallel execution are sufficient for most of the application. Okay? Now, do you remember this exploration? Okay, now, yesterday we observed that I have different parameters. I can go in breadth, I can go in depth, and now I can go in random. Okay? Now I add random. If you remember the difference between sub and mav when you consider all the properties of the widgets or only a subset of the properties of the widget when you combine the when you compare the GUI for understanding if they are equivalent or not. Okay, so I want to show you. I want to do some results that I obtained in the JSS paper, the paper where I presented the framework. That is the paper that I presented yesterday. And I want to ask you some questions. If I consider breadth first and depth first, from your point of view, which type of navigation covers more code? So, if I go in breadth or if I go in depth, which covers more code?
I can make a guess, but
Yeah.
but I don't have.
Yeah. From when I started this, I started the experimentation with an idea, and at the end of experimentation, my ideas were wrong. Okay.
I guess you don't have any difference.
No difference. From your point of view, if I go in breadth or if I go in depth, I have difference. No, great Stefano. I have no difference. Sub and math, in the sense, if I consider almost all the times that is sub, GUIs that are equivalent, or math may lead me to an explosion of the states, in the sense that 2 GUIs are all or are in most of the cases different. Which covers more code? Sub or math?
In this case, I guess it's math.
Yeah, in this case, math. Why? Because since in the sub is more restrictive, in the sense, if I consider 2 GUIs, usually these GUIs are considered as an equivalent, and I do not explore GUIs. Since for math, a new GUI is almost all the time different, probably I explore more, okay? And now, which is better? A systematic approach where I build a model, or if I go by random? Yeah, okay, I have an idea, I build the model, so I built the map of the ecological part. And the other part, we go together and we explore by random. Which is the best one?
My point is, it should be active learning. If it's not, you should throw that away because random is the baseline. If it's not better than random, you should not use it.
Yeah, but no, it's a problem because it depends. Because in active learning, at the end, I have also the model, so I have pros for using active learning. But in general, for you, which is better? Probably if I build a model, or if I go by random. If I go by random.
It's random.
Ah, great, random. You?
Learning.
Active learning. Stefano?
I guess it's active learning,
But it's random. If I go by random, okay, it is my experimentation. I have a lot of tricks to validity because I have to extend. We can change the models, but I tried to limit my tricks to validity. But I observed on 18 applications that random covered much more than active learning. As for the cost, the first and FTS are almost the same. As the cost, I intended the time of execution. As you can observe, guess, SAF is very, because it explores less, but it needs less time for finishing the execution because I explore states that are equivalent. Analogously, active learning is more cheap than random because random needs, as we saw before, resources and time. But okay, if I have resources and time, probably I can reach much more than an active learning testing technique. Thank you so much, guys. See you tomorrow. I don't know if there are some questions.
Not yet.
Okay. I believe that we have to leave the room to.
Yes.
There is a class now?
No. Yes, a class.
Okay, they have to.
Yes.
Okay.